Hi everyone. In this video we're going to go over benzene and its stability, and then we'll also talk about a rule called Huckel's rule, which will tell us whether a molecule is aromatic, anti-aromatic, or non-aromatic. All right, so let's start with an example here. We're going to draw an addition reaction. So we'll start with cyclohexene, and we're going to add hydrogen across that double bond. So we need a catalyst to help us with that reaction, and what we'll end up with is cyclohexane. Okay, so the enthalpy difference for this reaction is negative 120 kilojoules per mole. So the negative tells us that this is an exothermic reaction. Now, what if we try the same thing with benzene? Now, if we want to turn benzene into cyclohexane, we need 3 equivalents of hydrogen. We'll need to use a different catalyst, nickel, and we'll also need to perform this reaction at high pressure. So this is a little more involved than the previous reaction. Now, what would we expect the enthalpy change to be for this reaction? So looking up above, we said that adding hydrogen to a double bond is negative 120 kilojoules per mole. What about the reaction with benzene? Well, we're expecting 3 times the enthalpy change, right? Because we're adding 3 equivalents of hydrogen. So that comes out to be negative 360 kilojoules per mole. But when we actually run this experiment and do the measurements, the change in enthalpy is only negative 208 kilojoules per mole. So why? Why is this reaction enthalpy so much less than what we would expect? Well, part of that is due to the stability of benzene. So remember in our energy diagrams or reaction coordinate diagrams, we have our reactant with a certain amount of energy, and then we have our activation barrier, and then we get to our products. Now, if the reactants start out being unstable, so they're like way up here, for instance, so they have a higher energy, then the activation energy is less, but the enthalpy change is the difference between the energy of the reactants and the products. So that's a pretty large enthalpy, but if your reactant is more stable, then the delta H value is less. So the enthalpy difference here is due to aromatic stabilization. So remember, those 3 double bonds on the benzene ring are not localized, they're actually delocalized, and that stabilizes the molecule so it has a lower energy difference. Okay, so now let's talk about aromatic reactivity. So let's look at a different example of an addition reaction. So let's start again with cyclohexene. And this time we're going to add bromine across the double bond. So we know that this is an anti-addition reaction, so the bromines will add anti to each other. and will also form the enantiomer. Now, if we try the same thing with benzene, so let's say we try to add excess Br2, we actually don't see any reaction. And again, this is due to the fact that those pi electrons are delocalized around the ring. So let's draw benzene from the side. So let's pretend we're just viewing benzene from the side. So maybe I'll add some wedges up front so it's coming out towards us, some dashes in the back so that's going away from us. But each carbon in the benzene ring is sp2 hybridized. So that means there's an extra p orbital on each carbon. And I'll draw the blue and red lobes here so we can show that they're all aligned with each other. And again, the pi electrons are not sitting stagnant between two carbons. They're actually moving around the molecule. So we have delocalization above and below. So the p orbitals are aligned, and the pi electrons are delocalized. And that's what makes benzene stable. Okay, so now let's talk a little bit more about aromatic compounds. So we already said benzene is an aromatic compound previously, but we said earlier as well that there's a very specific rule for figuring out whether a molecule is aromatic or not, and we call that rule Huckel's rule. So we said that aromatic compounds have a very specific number of electrons, and that is 4n plus 2 pi electrons. So n can be 0, 1, 2, etc. So that would give us 2, 6, 10, 14, etc. pi electrons in our molecule. Now, there's actually another term which is anti-aromatic. And anti-aromatic compounds look pretty similar to an aromatic compound, except they contain 4n pi electrons, where n is 1, 2, etc. So you would have 4, 8, 12, etc. pi electrons. Now, there's also a few other parameters we have to keep in mind when we're trying to determine whether a compound is aromatic, anti-aromatic, or non-aromatic. So in the table below, we have parameters for aromatic compounds, for anti-aromatic compounds, and for non-aromatic compounds. So the first question we want to ask is the molecule cyclic? So do we have a ring system? If you do have a ring system, then your compound might be aromatic or anti-aromatic. We're not quite sure yet. If you don't have a cyclic system, then your compound is non-aromatic. All right, number 2. Does your molecule have a conjugated pi system in the ring? If yes, if there's a conjugated pi system, then it still could be aromatic or anti-aromatic. If you don't have a conjugated pi system, then it's non-aromatic. 3, is your molecule planar? If yes, then it's aromatic or non-aromatic, potentially. If no, then it's non-aromatic. And then finally, we're going to tally up how many pi electrons we have. If you have 4n plus 2 pi electrons, your molecule is aromatic. If you have 4n pi electrons, your molecule is anti-aromatic. And then for the non-aromatic category, the number of electrons isn't applicable. Okay, so again, in order for a molecule to be aromatic, so here we'll write a little checklist. It will be cyclic. It will have a conjugated pi system. It will be planar, and it will have 4n plus 2 pi electrons. If a molecule is anti-aromatic, it will be cyclic. It will have a conjugated pi system. It will be planar. And it will have 4n electrons, pi electrons. And then a molecule will be non-aromatic if it fails one of those first three tests. So maybe your molecule is cyclic and has a conjugated pi system, but it's not planar. Then it would be non-aromatic. Or maybe you have a molecule with a conjugated pi system that's planar, but it's not cyclic. So it just has to fail one of those first three parameters. All right, so if you're feeling overwhelmed and confused by Huckel's rule, that's okay. We're going to go over some practice problems. Okay, so I have this chart here, and we have 6 different molecules. The one on the end I drew in 2 different ways, just so you could kind of see what it looks like in 2 dimensions and then in 3 dimensions. And we're just going to go through each molecule and ask how many pi electrons it has, if it's planar, and then we're going to determine is it aromatic, non-aromatic, or anti-aromatic. So let's just go over the first one together, and then we'll pause the video so you can try the other ones on your own, and then we'll go over those together in a bit. All right, so let's start with the first one. How many pi electrons does the first molecule have? So there are 2 double bonds, and each double bond has 2 pi electrons. So that has a total of 4 pi electrons. All right, now is that molecule planar? Now, this is a tricky question because, for instance, without building the molecule, how do you know? Well, off to the very end, our last molecule is obviously not planar. Its ends kind of flip upward. So that is not a planar molecule, but I'll give you a hint. All of these other cyclic molecules should be planar. All right, I guess that's not a hint. It's more of giving you the answer. All right, and then finally, let's determine if this first molecule is aromatic, anti-aromatic, or non-aromatic. All right, so it has 4 pi electrons. Now, what we can do is test this out with the Huckel's rule we talked about. So we know that an aromatic compound has 4n plus 2 electrons. Now, we also know that n will be a whole number if this is true. So for our first molecule, we know that we have 4 pi electrons. So we'll set our 4n plus 2 equal to 4. And then let's solve for n. So let's see, if we subtract both sides by 2, we get 4n equals 2. And we'll divide both sides by 4, so n is equal to 1/2. All right, so that is not a whole number. And what we saw on the last slide is that n should be a whole number. So this fails the Huckel's rule test. So this is actually anti-aromatic. So it's still cyclic. It still has conjugated double bonds. And it's planar. But it's just missing that last component, the 4n plus 2 electrons. So it's anti-aromatic. Okay, so now I'd like you to pause the video and go through the other molecules on your own. See if you can figure out whether they're aromatic, anti-aromatic, or non-aromatic. And then we'll go over them together. So let's go over the second molecule. How many pi electrons do we have? So this one's a little tricky because we have that lone pair up above. So let's think about what the hybridization of that carbon is. So if we're focusing on the carbon at the top, is that sp, sp2, or sp3 hybridized? It's sp2 hybridized. And that tells us that the lone pair of electrons is in the p orbital that's left over when we have an sp2 hybridization. So electrons are in p orbital. Okay, so now that we know that, how many pi electrons do we have? 6. So we've got the 2 electrons in each double bond, and then the lone pair electrons are also in a p orbital. So are the electrons able to delocalize? Yes. So if we draw a little picture down below, each carbon has a p orbital because each carbon is sp2 hybridized. So the electrons can delocalize. All right. Now, the next question, is this molecule planar? And I already kind of gave you the answer. Yes, it is planar. So now we have to figure out, does this molecule have 4n plus 2 electrons? All right, so let's do our math down below, figure out if n is a whole number. So we'll set 4n plus 2 equal to 6. We'll subtract 2 from both sides, which gives us 4, and then n equals 1. So this is aromatic. Okay, let's go to the next molecule. How many pi electrons does that molecule have? Only 4. So we have 2 in each of these double bonds, but we don't have a lone pair up above like we did in the last molecule. So this only has 4 pi electrons. Now I already told you that most of these rings are planar, but now we have to figure out, do we have 4n plus 2 electrons? Now previously, when we looked at the first compound, we said that 4 electrons is not consistent with the Huckel's rule. So we know that this isn't aromatic, right? Because it only has 4 electrons. But another question we should ask is, are the pi electrons delocalized around the ring. So let's figure out, is this top carbon sp hybridized, sp2 hybridized, or sp3 hybridized? So we are able to move these electrons around, right? So there is resonance there, and that tells us that the carbon at the top is sp2 hybridized. But instead of a full p orbital, it has an empty p orbital. So let's draw a picture down below. So our main question here again is, do we have a conjugated system? And we do see that we can delocalize or move our electrons around to create resonance structures. And that positive charge is going to move around the ring. So we could do that another time and we could keep going. But the main point is, if we're focused on this top carbon, we can see that it is sp2 hybridized because we can delocalize those pi electrons around the ring, and it is going to be in a double bond part of the time. Okay, so we do have a conjugated system. All right, so that means that this is anti-aromatic versus non-aromatic. So remember, if we're going through that list on the last slide, is the molecule cyclic? Yes. Is it planar? Yes. And it has a conjugated system of p orbitals. The only thing it doesn't have is 4n plus 2 electrons. So this will be anti-aromatic. Okay, so let's go to the next molecule. So the next one looks very similar, but this time the top carbon has 2 hydrogens attached. Okay, so how many pi electrons do we have? Still just 4. Just those 4 in the double bonds. And we already said that the first few molecules are planar. So now we have to figure out, do we have an aromatic compound, an anti-aromatic compound, or a non-aromatic compound? All right, so we already said that if you only have 4 pi electrons, then that doesn't follow Huckel's rule, the 4n plus 2 rule. Okay, so now we just want to figure out, do we have a conjugated pi system? So let's draw a picture down below. And again, we have 2 hydrogens attached to the top carbon. Can we delocalize those pi electrons? No, because remember, to create a resonance structure, you either need to have a negative charge or a positive charge next to a single bond, next to a double bond. So those pi bonds are static. They're localized, they're not delocalized. And that top carbon is sp3 hybridized instead of sp2 hybridized. So it doesn't even have a p orbital that we could use to delocalize those electrons. Okay, so let's just write that down. Down below. So we cannot delocalize the electrons. Now, in the previous molecule, we could. Okay, so then would this molecule be anti-aromatic or non-aromatic? So it would be non-aromatic because we cannot delocalize electrons. So we do not have a conjugated pi system. So this is pretty complex stuff, isn't it? All right, it's a lot to keep track of. So let's go to the benzene ring. We know it's aromatic, right? But let's just go through the checklist to see why it's aromatic. Okay, so how many pi electrons do we have? 6, because we have 3 double bonds there. Now we know they're delocalized, but overall we have 3 double bonds. And is this a planar molecule? Yes. And are those pi orbitals, pi electrons, are they conjugated? Yes, we already said that they are delocalized, so this would be aromatic. Oops. All right, so now let's look at our last molecule. Now this one's a little funny looking. This was actually on the title slide for the lecture notes, and this is called octatetraene, or cyclooctatetraene. And I drew it from kind of the top, and if you look at it from the top, it does look planar, but if you look at it from the side, it's actually not planar. The two ends kind of flip upward towards each other, so we can just put a big old X in the planar column. Now, additionally, how many pi electrons does this molecule have? 8. So if we try to follow Huckel's rule, so 4n plus 2 equals 8, that means 4n equals 6, n would equal 6 divided by 4, which is 3 halves. So we don't have a whole number there. Now, it does look like those double bonds are conjugated, so they're alternating. However, because we don't have a planar molecule, this already becomes a non-aromatic molecule. Okay, so if we go back to our table, it is cyclic. It does have a conjugated pi system, but it is not planar, so it fails one of those 3 parameters at the top of our table. So it is non-aromatic. All right, so I think we'll stop there for this video. Your pod also asks you to kind of step through these different parameters to figure out if molecules are aromatic, anti-aromatic, or non-aromatic, but some of the molecules in your pod have nitrogen atoms or sulfur atoms in the ring, so that can make it a little trickier to figure out whether it's aromatic or not. So next time we'll talk about those types of ring systems that have non-carbon atoms, and we'll figure out whether they fall under aromatic, anti-aromatic, or non-aromatic. So I will see you then.